Okay, in last class we obtained the equation for bar element. The equation for bar element, if we consider this kind of bar element, let's take the cross-sectional area as A, the elastic modulus of the material as E, length of the beam is L. Okay, for this kind of bar element, we obtain a finite element equation using the using the basic Galerkin's method. So then this bar element we are representing using this kind of a line element. Okay, this kind of line element. Then we assign the coordinate system. So then each and every the forces acting on the element f1x, f2x in this kind of manner we can represent. Though if one element we can represent f1 and f2, the node 1, node 2. So then for this line element, single bar element, we obtain the equation. What is the equation we obtain? E divided by L, 1 minus 1 minus 1 1 u1 u2 is equal f1 f2. Okay, this equation we obtain using the Galerkin's basic finite element modeling approach. We obtain actually this term is called the stiffness. This term is called the stiffness. So if you take the bar element, this term actually represents the stiffness. How it becomes the stiffness, I will explain that one. Let's take the certain bar element is subjected to a certain force F. Okay, then the stress develop in this bar element due to the external forces. Let's take it as sigma. Sigma is equal E into epsilon. We can relate stress developed in this bar element with this equation. Sigma is equal to E into epsilon in the proportional region. So then sigma, we can call it as a F divided by A into E into the what is strain delta L extend length divided by the original length. Okay, then if you can make this term, yeah, I'm going to take the f into subject in this here, in here. Okay, f is equal E divided by L into delta L. Okay, actually this equation is similar to f is equal kx. No, if we take the spring, okay, if we take the spring, x representing the external length, then the k is representing the stiffness of the spring. Okay, similarly in here the bar, for the bar element, this term is representing the stiffness of the bar. Okay, delta L is the external length. Okay, delta L is the external length. So from the further examples, I am using for this term I am using the k, stiffness. Okay, so then this equation we can rewrite including the stiffness of the bar like this: the k minus k minus k k. So then I'm going to use for the displacement I'm going to use the letter D. Okay, don't worry about that one. D1 D2 is equal F1 F2. Okay, this is called stiffness matrix. Okay, this is called element stiffness. If we are defining this stiffness matrix, actually this element stiffness matrix called matrix, nodal displacement matrix. This is called a force matrix, that means the nodal force matrix. Okay, in this way we can this is called stiffness matrix, then the nodal displacement matrix, the nodal force vector, nodal force matrix. We can, this is the basic equation we are obtaining for the bar element. Here this is a K mean the stiffness of the bar. Okay, then now we are going to discuss how this is basic equation used to model the complex bar assemblies. Okay, let me take the bar assembly, then let's understand through the example. This one, let's understand through the example. Okay, then let's take the bar 2 assembly. That means this assembly contains the 2 bar elements. Okay, let's take the different cross sections. Okay, then it is subjected to a different forces. Okay, let's take this one is yeah, let's take this point F1, F2 and F3. Okay, this bar element is subjected to a, let's take this one as A1, this one as A2, then length L1, length L2, okay, then the elastic modulus also we have taken E1, then this one is E2. Okay, the bar assembly is given. The bar assembly is given. Okay, then the bar assembly is given for the entire bar assembly. Now what we are going to do, for the entire bar assembly we are going to do the finite element model. Okay, that means by discretizing the domain we are going to represent that the discretized model as to each and every element we are going to represent by a line element. Okay, line elements, because all the forces acting in axial direction, so then it is easy to use the line element to represent this one. So that means I'm going to use the 2 line elements, okay, to represent this first bar and the second bar. This one is called the first element. Okay, this one is called the second element. Okay, this one is called the second element. So then the forces acting on this element we can represent in this manner, this kind of manner. F1, that means the forces acting on these nodes, external forces acting on this node, the capital F1, capital F2 and the capital F3. Okay, so then sorry, before we want to assign the coordinate system. Okay, because it is a linear, so I'm going to assign the coordinate system in this kind of direction x. Okay, so when assigning the forces, we are writing F1 x, that means force acting in x direction, this one also x direction, this one also x direction. Okay, okay, then this is the node numbers also we have to include, node 1, node 2 and the node 3. Okay, here you can see the finite element model we that means the discretized model we create based on this given assembly. Okay, element 1, element 2, node 1, node 2 and node 3. This is the coordinate system. Then these are the external forces acting on, we are representing like this. Okay, this is the finite element model we drew for this bar assembly. Okay, the another thing we have to represent also stiffness of the first element and also the stiffness of the second element. Okay, here the K1 is equal A1 E1 divided by L1. The K2 is equal A2 E2 divided by L2. Okay, L2. Then this model I am going to discretize this the element wise. That means I am going to represent this assembly by a element wise. That means if we take the element 1, this is called a two element model. Element 1. Okay, I am going to draw the free body diagram for the element 1. If you take the element 1 separately, what are the forces acting on it? Okay, then this is the element 1. Okay, then this is the node 1, node 2. Then in this model, one thing we see, the displacement also we have to represent in this diagram. Okay, T1 x here, D2x here, D3x. Okay, sorry, that means the displacement, the nodal displacement is equal d1x, nodal displacement at the node 2 is equal d2x, nodal displacement at node 3 is equal d3x. Okay, okay. Then stiffness K1. Then the forces acting on this first element on node 1 we are representing in this kind of manner. Okay, F1x1. Okay, the forces acting on the second node, first element second node, we are representing, sorry, like this, F2x1. Okay, you can see the we are using the three letters. That means if we take the F2x1 mean this the two subscript letters representing this one representing the direction where it is acting. Then this letter subscript letter represents the node which is acting, and this one is representing the element. This one is representing the element. Okay, the same as we can represent the nodal displacement. Here the nodal displacement d1 x, but no need to represent the element wise. Okay, anyhow I'll represent that one later. I will explain it. D2x 1. Okay, this is the element 1. If we take the element 1 free body diagram. Okay, the element 2 free body diagram. Element 2, for the element 2 also we can draw this kind of diagram. The element 2, okay, this is how we are represent the element 2. Then node 2, node 3. Then the stiffness, the K2. The nodal force. Here, what is the subscript letter? Node 2. What is the direction? X direction. What is the element? Element 2. Okay. Then what is the node 3, direction X, element 2. Okay. Then nodal displacement also. Node, direction, and the element. Okay. D, node, direction, and the element. Okay. In this kind of manner, we can represent all the element forces and the element nodal displacements. In here, the thing is because it is a line element, these values are equal. That means if we take these values separately, that means for the bar assembly, and for the element wise, d1x in 1 is equal d1x, d2x 1 is equal d2x 2 is equal d2x. So d3x2 is equal d3x. Okay. So instead of this we can put the d1x. Instead of these two we can put the d2x. Instead of this one we can put the d3x. But here the forces are different. Okay. Then so I'm going to write the element 1 equation. Okay, see the element 1. Then these are the nodal forces, and the displacements are known. Then the stiffness also known. So the element 1 equation I'm going to write. Element 1 equation. Okay, element 1 equation. The element 1 equation is equal. So we obtain the element equations using the basic method. So I'm going to use that equation directly. F1x1, F2x1, k1 minus k1 minus k1 k1. I'm going to put the d1x here, d2x, okay, without putting okay. Then I'm going to write the element 2 equation also. Element 2 equation. Element 2 equation we can write f2x2, f3x2 minus k2, sorry, plus k2 minus k2 minus k2 a2, d2x, d3x. Then these are the element equation we obtain based on this model. Okay, so then to obtain the global solution, okay, global equation, to obtain the global equation, these are called the element equation. So by assembling these two we can obtain the global equation. Okay, to obtain the global equation I am going to assemble these two equations to obtain the global equation. Then how to assemble these equations? Okay, there's a various method to assemble these equations. So I am going to use the basic method, nodal equilibrium method, to assemble these equations. That means I am going to consider the equilibrium of the nodes to assemble to show this assembling process. By considering the equilibrium of the nodes, we can assemble these equations. Okay. So then I am going to consider the equilibrium of the node 1. First I am going to consider the equilibrium of the node 1. Okay. This method considering the consider the equilibrium of nodes. Consider the equilibrium of nodes. We are going to assemble these two equations. So how to assemble these two equations? Let's see. Okay, so I'm going to take the here first element. Let's take this is the first element. In this method, to understand this method, here this is the element we are representing this bar. This bar is represented by this kind of a line element. These are called nodes. Okay. Then I am going to separate this dot from the line. Okay. To understand this method, I am explaining in this kind of manner. Okay. Then I am going to consider the equilibrium of this node dot. Okay. That means I am going to consider the equilibrium of this node. Okay. If we consider all the forces acting on this node. What are the forces acting on it? Node? Okay. What are the forces acting on this node? Okay. Here, this is the external forces acting on it. Okay. I represented that one F1x. Okay. External force acting on it. Okay. Here we represent here F1x 1. That means the force acting on the line from the dot. Okay. This force is the force acting. We can consider this force as a force acting on this line from the node. Okay. This force is representing which is acting on the line from the node. Okay. So then what is the force, reaction force acting on the node from the line? Equal to magnitude is equal to this one, but opposite in direction. So that if you take the first node, we are representing this reaction force in this kind of manner. F1x1. Okay. Here the node 1. Okay. Node 1. Similarly, we can write the free body diagram for the node 2 also. If we take the node 2, okay, what is the external force acting on it? Okay, what is the external force acting on it? In this direction, capital F2x. Okay, then the two forces are acting on the nodes. That means from the element 1 and the element 2, the two forces are acting. Okay. Okay. Then this force is representing the force acting on the line from the node. So this force, if you take the force acting on the node from the line, that should be opposite in direction. That should be opposite in direction. That means this is acting in this direction. It is equal to F2x1. Okay, F2x1. Okay, then this is this one. Okay, this force acting, this force is representing force acting on the line from the dot. Okay, so that what is the force acting on the dot from the line, that is the opposite in direction. That means the reaction force of this one. Okay, that is acting in this direction. What is that? F2x2. Okay, this is the node 2. Then I'm going to consider the node 3. Okay, on the node 3, what are the forces acting on it? In this direction, F3x is acting. Okay, F3x is acting. So in another direction, F3x2 is acting. Okay, these are the free body diagram for the each and every nodes. So then I am going to consider the equilibrium of these nodes. Okay, I am going to consider the equilibrium of these by writing the equilibrium of these equations. For the node 1, we can write the F1x is equal F1x1, F2x is equal F2x1 plus F2x2. Then F3x is equal F3x is equal F3x is equal F3x2. Okay, this is the equilibrium of these nodes. Okay, then these equilibrium equations we can further equal from these elements. What is F1x? From this equation, F1x is equal, if you take for example F1x1 is equal K1 D1x minus K1 D2x. Okay, instead of this one, I am going to write k1 d1x minus k1 d2x. Okay. Similarly, here if 2x1, if 2x1, this one is equal to minus k1 d1x plus k1 d2x. For this one, plus no, yeah, k2 d2x minus k2 d3x. Okay. For this one, minus k2 d2x plus k2 d3x. Okay. Then we can write the equilibrium equation by considering the equilibrium of the nodes in this kind of manner. So then we are having the three equations. Now we are having the three equations. These three equations I will rearrange. I will rearrange these equations by simplifying. If 1x is equal k1 d1x minus k1 d2x, there's no d3x terms. I will also include that one, d3x. Then if 2x, so what is it, minus k1 d1x plus k1 plus k2 d2x minus k2 d3x. For the f3x also we can write 0 d1x minus k2 d2x plus k2 d3x. Okay. In this kind of manner we can write the equilibrium equation considering the nodes. Okay. So then I'm going to put all of these equations into a matrix form. Okay. I'm going to put these equations in a matrix form. I will write in that view also. Okay. Yeah. I'm going to put all of these equations in a matrix form. Okay. So then global force vector, sorry, f1x, f2x, f3x is the global force vector. Then the global stiffness matrix k2 0 minus k1 plus k2 minus k2 0 k2 k2. This is called the global stiffness matrix. This is called global nodal displacement matrix d3x. Okay. This is called global nodal force matrix. This is called global stiffness matrix. This is called global nodal displacement matrix. Okay. In this kind of manner, we can assemble the element equations. We can assemble the element equations. That means this element equation, by writing the after writing this element equation, we can assemble to obtain the global solutions. Then after if you are having this global equation, Then next step we have to substitute the boundary conditions, known values of the displacement, known values of the forces. By substituting the known values of the forces, we can solve for unknowns. Okay. Then to obtain this global equation, there's another easy method. This one also easy method. Consider the equilibrium of the nodes. There's another easy method called direct stiffness method. Okay. Then further there's a simplified method called simplified direct stiffness method. So okay, I will explain that simplified direct stiffness method to assemble these element equations to obtain the global equations. Okay, then if we are having the stiffness matrices, okay, element 1 stiffness matrix and the element 2 stiffness matrices. Okay, I'll write that one. Element 1 stiffness matrix. Okay, element 1 stiffness matrix. Let's take the K1. Okay, K1 minus K1 minus K1 and the K1. Okay, then the element 2, write that one here. Element 2 stiffness matrix. Okay, the K2 is equal, simple K2, K2 minus K2 minus K2 K2. Okay, then if we can write the global stiffness matrix using these element stiffness matrices, then we can easily write the global equation by relating the nodal forces with the nodal displacements. Okay, then here I am explaining the easy method to obtain the global stiffness matrix from the element stiffness matrices. This method is called simplified direct stiffness method. Okay, this method is called simplified direct stiffness method. Okay, then very easy method. I will explain that one. Okay, then if you take this element 1 stiffness matrix, you can see this element 1 stiffness matrix. This column always multiply with the d1x. So I am giving the name for this column as the d1x. This column always multiply with the d2x term, so I am writing top of this column as the d2x. Okay, then here the d1x and the d2x terms, I will write that one also, d1x and the d2x. Okay, here you can see the column and the row we have named in this kind of manner, because this is multiplied with the d1x term, this is because multiplied with the d2x term. I will write that one. Here also we can write we can name this one. Here this column always multiply with the d2x term, this one multiply with the d3x, then d2x and d3x. Okay, then this is okay, then here we are having the three nodal displacements. That means for the nodal displacement matrix, d1x, d2x and the d3x. So our global stiffness matrix should be a 3 by 3 matrix. Okay, that means I'll name this global stiffness matrix in this kind of manner: d1x, d2x, and d3x. This column also d1x, d2x, and the d3x. Okay, this kind of manner we can represent the global stiffness matrix. So then these are elements. It's a 3 by 3 matrix. This element I'm going to explain how to obtain these elements. Okay. 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 Then here the d1x. You can see this is the column number, this is the row number. If you take this term, you can say the d1x into d1x terms should be included in this position. Okay. So what are the d1x term we can find from these two stiffness matrices? Okay. Here the d1x. Okay. There's no any other d1x term, so then we can put the k1 in here. Okay. Then d2x d1x terms. Okay. We are studying from this column number and the row number. d2x d1x terms. What are the d2x d1x terms in this matrix? Okay, here the one, no, d2x d1x. There's no d2x d1x any other d. So that means that is equal to minus k1. Okay. Then d3x d1x. Is there any d3x that means d3x d1x terms? d3x d1x, no, 0. Okay. Then we are going to next row. That means for the next row, d1x d2x terms. d1x d2x terms. What are the d1x d2x terms? d1x d2x term here is a minus k1, no, minus k1. Then d2x d2x terms. d2x d2x terms. So what are d2x d2x terms? Here there's a 1, here there's a 1, k1 plus k2, k1 plus k2. Okay, the two terms, because that's why we are putting in this kind of manner. Okay, by adding these two we can put it. So then d3x d2x terms, d3x d2x terms, minus k2. Now d1x d3x terms, 0. d2x d3x terms, d3x d2x terms, sorry, this one, no, minus k2. d3x d3x term, k2. Okay. Then this is how we obtain the global stiffness matrix. If we know the global stiffness matrix, we can write the global equation by relating the nodal displacement with the nodal forces. Okay. That means I will write that equation also by relating this. By looking at this equation, we can write the global equation. If we know the global stiffness matrix, we can write the global equation by relating the nodal displacement and the nodal forces. So I will write that one also. And now we can relate these equations. That means we know the global forces as F1x, F2x, and the F3x. Okay. Then we are going to relate these forces with the nodal displacement d1x, d2x, d3x using the global stiffness matrix. Okay, what is the global stiffness matrix? This is the one you obtain using the simplified direct stiffness method. Okay. Okay, this is the equation. Okay, this method is very easy to obtain the global equation using the to that means the stiffness. If we know the stiffness matrices for each and every element, we can easily obtain the global equation. That means we can easily write the global stiffness matrix using the simplified direct stiffness method. Then we can easily write the global equation for this in this kind of manner. Okay. Then up to now you know the simplified direct stiffness method and how to assemble these equations. Then another important thing I have to explain further, the boundary conditions. Then after obtaining these equations, we have to substitute the boundary conditions. What are the boundary conditions at the that means the known values at the boundaries. So that means the known values of the nodal displacements, the maybe the known values of the forces we have to substitute in this equation. Then after substituting these known boundary conditions, we can solve this equation to find the unknowns. Okay, so let's say if you take the boundary conditions, there's a two type of boundary conditions. The two type of boundary conditions called homogeneous boundary conditions and non-homogeneous boundary conditions in two type of boundary conditions called the homogeneous boundary conditions and the non-homogeneous boundary conditions. So what is the difference between these two? The non-homogeneous boundary conditions allow some finite displacement. For example, if you take a certain node, that is this non-homogeneous boundary conditions representing in this kind of manner. This is okay. For example, delta x. Okay. For the node 3, this is the non-homogeneous boundary conditions. Okay. This non-homogeneous boundary conditions, when the structure loading, it will allow delta x displacement. Okay. It will allow delta x displacement. Then it definitely displays the delta x amount when it loading. Then at this position it will settle. Okay. This is called the non-homogeneous boundary conditions. Okay. But in homogeneous boundary conditions, this completely prevent the movement. Okay, at the boundaries, the displacement, that means they completely prevent the displacement at the homogeneous boundary conditions. Okay, non-homogeneous boundary conditions, that will allow some displacement up to settle. Okay, then this is the difference between these two. Okay, then another important thing I want to say about this stiffness matrix. If you take this, if this is a matrix that is symmetric around this diagonal. Okay, it's a symmetric matrix. There is an important property of this stiffness matrix for any assembly. It's a symmetric around this diagonal. Okay, there is also very important property. Then after obtaining this global equation, next step is to substitute all the known forces and the non-nodal displacement. Okay, for example, if this is fixed at these 2 points, okay, let's take at these 2 points that is fixed. Okay, then yeah, then how to substitute the boundary conditions. Okay, at these 2 points are fixed, then the let's take the P force is acting. So then how to substitute the boundary condition for this equation? Okay, I will write that equation, substitute the boundary conditions. So then you can see the nodal force vector. So then F1 is an unknown reaction from this fixed support is unknown. Then the P force, that means F2 x is equal to the p force, the force acting at the middle portion. It's a known value, the given, the p. Then f1 x, f3 x, that one also unknown. It's a reaction from this fixed support. Okay. Then the global stiffness matrix, k1 minus k1 0 minus k1 k1 plus k2 minus k2 0 k2 k2. Then d1x, sorry, here what is d1x? The d1x, if this is a fixed support, the displacement should be 0. It's a homogeneous boundary condition that will prevent the displacement at the nodes. So sorry, this one should be equal to 0. Okay, this one should be equal to 0. Then the d2x, we can't, it's an unknown. Okay, d2x we can't say it's a non-zero value, we don't know. So but in d3x we can definitely say that will equal to 0 because they at the fixed support. Okay, in here you can see, after substituting the known force values and the displacement boundary conditions, we are having this equation. In this equation, these are unknowns. Okay, this one is unknown, this one is unknown, and this one also a unknown. Then this one is a known. Then the k1 and k2 are known values. That means the properties of the bar elements. That means the stiffness of the bar element, each and every bar element is a known value. So then in these equations, we are having the three unknowns. We are having the three equations that we can find the unknowns. The d2x, f1x, and f3x we can easily calculate. Okay, if you know these force values and the displacement, we can calculate. We can write the equation for sigma, that the stress developed on the each and every bar element we can calculate. Okay, then this calculation I will explain in later topics. We are discussing how to calculate the stresses in stress developed in each and every bar element for this kind of bar assembly. Okay, the enough for today, enough for this lecture. The next on next lecture we are going to discuss some example problems, numerical valued example problems related to these calculations. Okay, thank you.